This slideshow explains earthquake intensity. Intensity is not the same thing as magnitude, even though we commonly use these words to mean about the same thing in colloquial speech. Remember, magnitude of an earthquake is a measure of the strength of the earthquake and can be related to the energy released. Intensity, on the other hand, is a measure of the felt effects of an earthquake, which varies from place to place. An earthquake can have only one magnitude, but has many different intensities depending on where the earthquake waves were felt. The earliest attempt to qualify intensity was based on, well, what people actually felt or observed. The scale based on observations is called the Modified Mercalli Intensity Scale, and it ranges from Roman numeral 1 to Roman numeral 12. The Roman numerals are used so you don't confuse magnitude with intensity. Earthquakes need to reach intensity 2 before people begin to sense them, and then only people in very quiet environments would probably even notice. By intensity 6, everyone feels the earthquake and it goes downhill from there. The highest intensities are based on observations of damage produced by the earthquake, such as toppled buildings or bent railroad rails. We can only imagine what Mercalli meant by total destruction. In recent years, there's been an attempt to quantify intensity by associating each level with an amount of ground acceleration, which I've shown here in the yellow column. The ground acceleration is expressed as a percentage of g, the normal gravitational acceleration on the surface of Earth. One way to think about this is that if there's a vertical ground acceleration greater than 1g, then objects on the ground will be literally propelled into the air. This actually can happen with the largest earthquakes with intensities larger than 11. Nowadays, intensity maps are often created by crowdsourcing. For example, the 2001 Nisqually earthquake in Washington produced effects that were felt over a large area around Seattle, and people emailed in answers to a USGS questionnaire about their experiences. This map was made from over 12,000 responses and shows the distribution of intensities produced by the earthquake. The USGS is working on implementing an even faster response time for making shake maps using computers to synthesize tweets sent in by residents. It's probably obvious that intensity varies with location because of earthquake wave attenuation. Locations farther from the epicenter will be less affected because the waves will have died out. But it turns out that it can be a lot more complicated than this. For example, here's an intensity map for a strong earthquake that struck the New Madrid Fault Zone in Missouri in 1811. Since it was 1811, the intensity map was determined from written accounts of the earthquake, which included church bells ringing in Boston over 1,000 miles away. Now compare the distribution of intensity produced by the much larger 1906 San Francisco earthquake. Even though this earthquake was larger, it was felt over a much smaller area and to a much smaller degree. What's going on here? It turns out that this is a great example of one of the most important controls on intensity, the overall strength of the rocks in the area of the earthquake. The eastern part of the U.S. is geologically old. The most recent mountain building event occurred over 200 million years ago, and since that time the crust has been simply eroding. Old crust is also relatively cold crust because it lacks igneous activity that can heat it up. In contrast, the western margin of North America is an active margin shown by the yellow line and has been active for many millions of years. This activity has produced faults, mountains, and intrusions of magma which have heated up the crust. As a result, the crust out west is relatively hot. Seismic waves travel a lot more easily through cold crust than hot crust because cold crust is denser. It's the same thing with sound waves. They travel more easily through a dense substance like metal than a low-density material like foam. This is why foam insulation is often used to baffle sounds in rooms. So the waves from an earthquake in the east will attenuate a lot more slowly than an earthquake from the west, producing a larger footprint of effects. Here's another curiosity. Look carefully at the intensity map for the 1906 San Francisco earthquake map in a little bit more detail. As we'd expect, in general, intensity decreases away from the epicenter, but notice that it's not that simple. There are hot spots where the intensity is abnormally high, such as right here. The intensity here is higher than it is at some locations closer to the epicenter. What's going on here? The answer is that the amplitudes of shaking have been intensified in this area due to the makeup of the geologic materials, and that these more intense waves produce more effects. This phenomenon is called amplification. It typically occurs in loose sediments that have accumulated as thick layers in a sedimentary basin, which is often a depression in hard, crystalline, igneous, or metamorphic rock. So you have a stark contrast in material properties: hard, dense, igneous rock surrounded by loosely compacted sediment. Seismic waves carry energy, and this energy is expressed in two forms: kinetic energy, which depends on the speed of the wave, and elastic energy, which is stored in the material vibrations. And just like with water waves, when a seismic wave slows down, it loses kinetic energy and has to compensate by increasing its amplitude. With seismic waves, this causes the amplitude of shaking to increase as the wave slows down. Waves travel more slowly through loose sediment than through solid rock, so when waves enter the sediments of a sedimentary basin, they slow down. And when they slow down, they convert kinetic energy into elastic energy in the form of increased amplitudes of vibration. In other words, the shaking gets more intense. This short animation created by Iris does a great job of showing the effects of sediment amplification of seismic waves. If you look carefully, you can see the seismic waves slow down as they enter the poorly consolidated sediment and water-saturated sand and mud, and at the same time the amplitude of shaking increases. This effect is most apparent for the more slowly moving S and especially surface waves. The three seismograms at the end show how much amplification occurred. A great example of this effect can be seen in the shaking produced by the Nile. Here's an example. The Marina district was heavily damaged, while the adjacent Fort Mason was hardly touched. This difference was due entirely to sediment amplification of seismic waves.